Well, 8 o'clock here in London on a cold, frosty morning. It's going to be a nice day, I think. So, good morning to those of you in Europe and Africa, and good afternoon and evening to those of you joining us from Asia. And a very warm welcome to you all. Thank you for joining this, the 38th of our regular series of short courses on pumping topics, and the first one of 2025. As you see, I'm sporting my brand new waistcoat and tie combo that my wife bought me for Christmas. So you're honoured. This session will last about 40 minutes, allowing us plenty of time for a Q&A session at the end. Here's a listing of the previous short courses we've run during the last year. If you've missed any of them, you can get a copy of the materials at our website. Go to www.ruhrpumpen.com and follow the link to the RP short courses. Here's the page you get to if you go to ruhrpumpen.com. It's the home page, and here is the link on the top menu bar to RP short courses. If you click on that, you get to this screen, and you'll see all of the recent courses listed. Here are the latest 4. And you can click on any one of them to see the course material and download copies for viewing at your leisure. Just the other day, I requested some data on the number of downloads we've had for these sessions, and I was very gratified to see these numbers. Some 10,000 downloads for some of the earlier sessions that have been out there for a while. I think I'm rapidly becoming an influencer. Well, this is what we're covering today: the beginner's guide to startup, commissioning, and troubleshooting centrifugal pumps. Now, a 1-hour session is most certainly not going to turn you into a qualified commissioning engineer, but it will point you in the right direction and enable you to have an intelligent conversation with a commissioning engineer. I'm indebted to Jennifer Knox and Ian James for the vast majority of this material. We'll be holding a Q&A session at the end, as usual, so please use the Q&A session at the facility at the bottom of your screen to ask any questions or make any comments. And you can do that at any time. I'll address those that I can live at the end of the session, and the rest I'll address by mail in the coming days. We are recording the session and we'll make it available as a YouTube link, as well as by emailing you a PDF version of the slideshow and of the Q&A summary from both of today's sessions. Well, here's a summary of what we'll cover in today's session. What is commissioning and startup? General precautions and checks, the procedure, commissioning checklist. Then we'll move on to troubleshooting, what it is, basic requirements for trouble-free operation, 5 common problems, some flow diagrams and charts, then checking 5 major pump parameters. Then we'll move on to seals, common reasons why seals fail, the types of failures, and some troubleshooting on seals. So first, commissioning and startup. This is the final step before production runs in a processing plant. Project commissioning is the process of assuring that all systems and components of a building or industrial plant are designed, installed, tested, operated, and maintained according to the operational requirements of the owner or final client. The picture shown here is a Ruhrpumpen crude oil pump commissioned in India, supplied to India's largest oil and gas PSU in East India. So startup and commissioning are essentially the same. It takes steps to properly prepare the equipment for startup and eventual commissioning into fully operational process conditions. Once it's up and running, it's brought up to operational conditions and run for a period of time, maybe days, to ensure there are no issues. And if any problems do arise, then we start the troubleshooting process. So, number 2, general precautions and startup checks. First, rotate the pump shaft by hand. It should be free to turn with no rubbing. Now, on a small pump, you may be able to turn it literally by hand. On a larger pump, you may need to use a pipe wrench on the coupling spacer. Check the driver for correct rotation. It's important to check the driver rotation to make sure it matches pump direction of rotation arrow that's engraved on the pump casing. In some cases, pumps may operate in reverse, and that could be running at about a third of the design performance. Now, it may sound obvious, but it clearly isn't. I spoke to a friend of mine who is a commissioning engineer at Elliott Ibarra, and I asked him, how often do pumps get wired the wrong way? And he responded, more often than you can possibly imagine. It's unbelievable how frequently this occurs. It's good practice to flush the piping of the system in which the pump is to be installed, the suction and discharge piping of the pump. During commissioning, there's usually a lot of crud left in there, and there'll be bolts and weld rods, all sorts of things will be in there. So give it a good flushing, because you don't want that going through the pump. If you're operating above about 90 degrees centigrade, 200 degrees Fahrenheit, you need to warm the pump up before starting. So use the warm-up lines and allow ample time for the pump case to heat up. You do this in general terms. You circulate a small amount of fluid through the pump from the drains connection up through the discharge, and circulate it until the casing temperature is within 38 degrees or 100 degrees Fahrenheit of the fluid temperature prior to pump startup. And this will avoid thermal shock to the casing and impeller and prevent damage of the mechanical seal. Now, you won't need to do it every time. It's only if your temperatures are above about 90 degrees centigrade. And the hotter it is, the more important it is to follow the IOM directions. Each pump vendor might have slightly different instructions for different pumps at different temperatures. The hotter the pump, the more important it is. Number 5, don't operate below minimum continuous flow, as shown on the performance curve. You can start the pump up at closed valve. That's the normal way of doing it, starting the pump at closed valve, but immediately open the discharge valve and bring yourself onto the operating curve. Typically no more than 15 or 20 seconds at shut-off. Some checks for the mechanical seal. Well, what I show here is pretty generic. Check the seal IOM for individual requirements. This is from an Eagle Bergman IOM for their non-API seal. Seal assembly fixtures. They provide for holding the cartridge seal in one piece during transport, storage, assembly, and removal. They must be removed before startup. Check the pipe connections. Seal flush, quench, leakage plan. Check your disposal connection. The disposal, that's the seal leakage connection, say a plan 65 if you've got a seal leakage plan. Check the rotation of the seal matches the rotation of the pump. Depending on seal design type, if seals run in reverse, the seal could be damaged or leak. And heat generated by an improperly installed seal could incur further damage to the pump. Now, a lot of mechanical seals are bidirectional. They'll run in either direction, but in some cases they are unidirectional, and you need to check the drawing to check that they've been properly installed. This is important. The pump should be installed and properly grouted to the foundation, assuming it's a grout type base plate. Properly anchored equipment, well, that will eliminate potential vibration, which could cause premature seal failure. Flush the pump and seal area with pressureless flushing medium. Get all the crud that's in the piping system away from your mechanical seal. And thoroughly vent the seal chamber to remove entrapped vapors. Otherwise, the seal face temperature could rise due to insufficient lubrication, which could damage the seal. Number 3, startup procedure. Now, this really shouldn't need saying, but it does. You know the old adage, finally, if all else fails, read the instruction manual. Well, we prefer you to read it in advance. And the other thing you need when you do the commissioning is you must have the pump curve there. We'll come to that. So here's the procedure. Before starting the pump, check the security of all bolting, piping, and wiring. Check gauges, valves, and instruments. Check all equipment for proper lubrication and correct rotation. Open the oil fill and breather connection to verify that the oil rings are in their grooves. Check that the discharge valve is closed. Then open the suction valve. Crack open the discharge valve, but don't fully open. Partially closed discharge valve will also prevent initial cavitation. Allow the pump to fill with fluid if the pump is self-venting. And for non-self-venting pump, you need to vent the case and the seal chamber, opening the vent at the top of the pump casing until all air is expelled from the casing. Keep these valves open for approximately 60 seconds to ensure the pump is completely full of fluid, then close the discharge valve. Uncouple the driver and the pump from the pump, then start and then immediately stop the driver. It's a bump start, and observe the rotation of the shaft. The correct rotation should be in the same direction as the rotation arrow engraved on the pump casing. And if the shaft rotation is incorrect, you've probably wired it wrong. You've probably switched the live and neutral. Once priming is accomplished and correct shaft rotation established, you're ready for startup. So securely couple the driver and the pump again. Ensure the discharge valve is open to approximately a quarter of fully open. Start the driver again, and as soon as possible, completely open the discharge valve. Don't allow it to remain closed for any length of time, no more than 15 or 20 seconds. Pumped fluid temperature will rise excessively otherwise, causing damage to the pump. If the pump fails to reach the correct pressure, then we start the troubleshooting steps. And once it's running smoothly, we perform all the operating checks. So here's the commissioning checklist. Now, most of these are double checks, tasks which should already have been carried out and checked during installation long before startup. I won't read these out. Here's an extract from the IOM of an OH2 or BB2 pump. It's a little small and tricky to read right now, but it basically repeats what we covered in the last couple of slides. I'll leave it on the screen for a few seconds for you to look at, and I'll have a slurp of my cup of tea. So on to troubleshooting. The first step in troubleshooting is gathering information on the issue, such as an undesired behavior or lack of expected functionality, maybe noise, maybe vibration, maybe lack of flow. Other important information includes related symptoms and special circumstances that may be required to reproduce the issue. For example, if it's a vibration issue, maybe it only occurs at higher flows, for example, or lower flows. Once the issue and how to reproduce it are understood, the next step might be to eliminate unnecessary components in the system and verify that the issue persists, to rule out incompatibility and third-party causes. So, for example, if there is a bypass line, maybe close that off to see what effect this has on the problem. A clear understanding of the concept of cavitation, its symptoms, its causes, and its consequences is very much essential in effective analyses and troubleshooting of the cavitation problem. Fortunately, we covered this in quite some detail in session 28, NPSH Made Simple. So you're all experts in this area, but just in case, go back and review that session. Cavitation sounds like a handful of gravel rattling around in the pump. So the first thing to establish is where are you operating on the curve? And this is why you must have the pump performance curve with you while you're doing commissioning. If you're running out here to the right of best efficiency point, you're in an area of classic lack of NPSH available cavitation. If you're running back here to the left of BEP, suction or discharge low flow cavitation is likely. Never operate continuously below the pump supplier determined minimum continuous flow. This will be shown on the performance curve that you've got. No more than a few minutes at a time, followed by a return to a higher flow. Here's a reminder. This is the classic lack of NPSHA cavitation. Occurs on the underside of the impeller, the suction side of the impeller. Cavitation is the formation of bubbles or cavities in the liquid, developed in areas of relatively low pressure around an impeller, and as they migrate through the impeller towards the areas of higher pressure, they collapse with a shock wave, an intense shock wave, which can cause significant damage to the impeller and the pump housing. And this is suction and discharge recirculation cavitation. When you operate away from BEP, you will get recirculation vortices here in the suction and here in the discharge. These vortices result in low pressure areas where bubbles form and high pressure areas where they collapse. They form here and they collapse here. Form, collapse. Number 6, 5 common pump problems. No liquid delivery, low liquid delivery, intermittent or intermittent operation, low discharge pressure, and excessive power demand. So if you have no liquid delivery, it could be instrument error. Check them for errors or issues. Could be that the pump is not primed. If not primed properly, a pocket of air might be trapped in the pump, which will not allow centrifugal action to take place. Cavitation. Maybe you have severe cavitation. That will affect pump flow from the discharge. And here's an important one. Supply tank empty. Again, sounds obvious, remarkably common. Check the upstream tank. If there isn't a good level there over and above the NPSH requirement of the pump, then the pump may be wrongly accused of problems. Remember, commissioning is often carried out with a partially filled system, so it might well be that the supply tank is not full. Second one was low liquid flow rate. Again, instrument error, could be the beginnings of cavitation, early stage cavitation. There could be non-condensables in the liquid. Maybe there's presence of air from another line tied in on the suction side of the pump. And here's a common one on commissioning, inlet strainer clogged. As I mentioned, usually during commissioning, there's a lot of crud still in the pipework, so the inlet strainer might well be clogged. Intermittent operation or oscillating flow rate. Could be cavitation again. Could be that the pump is not primed properly. Check your priming procedures. And again, non-condensables in the liquid. Maybe there's a mix of liquid and air, which could cause intermittent or oscillating operation. Low discharge pressure. Instruments again. Non-condensables again. Speed could be too low. Maybe if the pump's working with a variable frequency drive, check the control of the VFD. And wrong direction of rotation. I mentioned earlier, if you're running the pump the wrong way, performance will be down to about 30% of what you'd expect. And interestingly, if it's a double suction pump, it's always possible that it's been installed, the impeller has been installed the wrong way round. That's another one to remember. Power demand too high could be caused by speed being too high. So check the speed of the motor, that it matches the pump, and check the control of a VFD if it's installed. The density of the liquid might be high. Check the supply tank. Maybe process fluid is getting mixed with other liquids. Maybe the tank is affected by cold temperatures. Maybe there are heaters on the suction tank which aren't operating. During commissioning, the plant might well not be up to temperature, so density might well be an issue there. See if the required system head is lower than expected. It might be running out on the curve or running back on the curve, depending on what downstream equipment is in line. The viscosity might be high due to malfunction of supply tank heaters. Again, during commissioning, you might not be at full temperature, so density might be high and viscosity might be high. The next few slides have some useful fault-finding charts. I'm not going to go through them in detail. They are self-explanatory. I'll leave each one on the screen for 20 seconds or so. You might well want to print this part of the presentation, and in fact the whole presentation, off when you get your hard copy of it, and keep it in your bottom drawer for troubleshooting. And the next section, checking 5 major pump parameters. Centrifugal pumps generally operate for years trouble-free. If there are problems, then there have probably been early indications that can help provide a solution. Knowing how to identify the many potential pump vibration causes will quickly lead to the potential culprit and solution. These slides are intended to give guidance as to the likely cause and the solution, and will assist operations, maintenance, and the pump and seal vendors' customer service guys to efficiently solve the problem. So vibration, power, flow, head, and temperature. First, vibration. Any attempt to solve vibration problems on pumps and motors should begin with a basic frequency analysis using a portable vibration analyzer. In most cases, a single vibration frequency will be dominant, often at rotating speed. Then, by a simple process of elimination, you can zero in on the source of the problem. Detailed spectral analysis is a specialist field. I'm not qualified to lecture on this, and it's well beyond this 40-minute short course. But this is the kind of analysis that a vibration specialist can offer you. If you're working for an oil company, you've probably got a vibration specialist there. Many of the larger pump companies will have a vibration specialist you can consult. And if not, there are various commercial enterprises that are able to do this for you. But here in the next 8 slides, I give you vibration analysis for dummies, a crib sheet to give you a clue as to what might be happening to your pump and to help you discuss the possibilities with a vibration expert. So looking at this first slide, vibration frequency in the range of 0 to 40% of running speed. Possible causes, 10% of the time, it's seal faces. 20% of the time, radial bearing damage. 90% of the time, thrust bearing damage. And 40% of the time, casing mounting bolts are loose. So this gives you a real clue as to things to check. And checking the casing mounting bolts is the first thing to check, as that can be done without taking the pump out of service and returning it to the workshop. It's a similar story here. Now, I'm not going to go through every slide in detail. You get the picture. I suggest you print out these 8 slides and keep them in your bottom drawer for quick reference if you need to speak to a shaky engineer, a vibration specialist. And same again here. I'll leave each one up about 20 seconds for you to have a brief read. This one's interesting. Frequency peaks at 1 times at the running speed. 90% of the time, it's an unbalanced rotating component or a bent shaft, and 40% of the time, misalignment. That's the quick and easy thing to check before you take the pump out of service. The vane passing frequency is the frequency at which the impeller vanes pass the volute lips or cutwaters. It's a possible design issue on a new installation. It's unlikely to occur as a matter of maintenance or wear. Very high frequency with peaks varying frequently, cavitation. So vibration was the first of the 5 major parameters. Number 2 is power. Fault finding, here's a fault finding flowchart for high motor current. And here, the possible reasons for an unexpected power increase. And the next one, possible reasons for an unexpected power decrease. And this, a fault finding flowchart for low flow or low head. And here, possible reasons for an unexpected change in flow or head. And finally, unexpected changes in bearing temperature. Up to section 10 now, common reasons why seals fail. A seal salesman once told me 90% of pump problems show up as mechanical seal problems, but 90% of seal problems are actually pump problems. Most often, a mechanical seal can be like a barometer for the pump, helping users to understand the state of health of the pump. At other times, failure is as a result of poor seal selection or seal installation errors. Here are some of the most common reasons mechanical seals can fail. Allowing your pump to run dry can be very damaging to a mechanical seal. Under the wrong conditions, mechanical seals can experience thermal shock and shatter within 30 seconds or less. Vibration. Pump vibration is caused by pump imbalance, improper alignment, operating the pump too far to the right or left of the best efficiency point. But vibration hurts your equipment and can result in damaged seals and shortened seal life. When rotating components are out of balance, the mechanical seal faces can separate because of the induced vibration and shaft runout. The seal faces can become damaged as the vibration causes the carbon face to bounce against the hard face, to chatter. When it comes to pumps, hammers are not your friends. Mechanical seal faces can be very fragile. Pounding couplings or bearings onto the shaft will damage your mechanical seal. Skipping initial startup procedures and installation errors are a big factor when it comes to mechanical seal failure. Improperly starting the pump can cause the motor to trip and the shaft to twist, causing orbital movement, resulting in internal part contact, seal failure, and shortened bearing life. An improperly installed mechanical seal will cause damage to elastomers, O-rings or boots, along with a wide variety of other issues, as pictured here to the left. Mechanical seals can be very sensitive because the faces are incredibly flat. Even a small amount of dirt or oil, even fingerprints, can cause the faces not to align. The picture to the right shows the spacer became lodged in the seal, damaging the internal components. Now, the installation instructions stated to remove these spacers before starting the unit. It's critical that a mechanical seal flush plan is properly in place. No mechanical seal recommendation is complete without a corresponding flush plan. Plan 11, 12, 13, 52, 53, etc. If no flush pan exists, then dewatered product and contaminants can build up, causing excessive heat or erosion on the seal, resulting in shortened seal life. Lack of knowledge and information accounts for the majority of mechanical seal installation errors. You must consider the normal operating conditions, the potential for off-design operation, and non-process activities such as cleaning, steaming, acid and caustic flushes. The picture here is an example of poor material choice for an abrasive liquid. Pump application engineers and salesmen should always consult the mechanical seal suppliers before quoting a pump. Always send the process and mechanical data sheets to the seal suppliers. And the same applies to EPC rotating equipment engineers. Before you specify a seal type, consult the seal vendors. Five types of sealing failures. Failure of the mechanical shaft seal is the most common cause of pump downtime, here in blue. The shaft seal is exposed to widely varying operating conditions, and sometimes operating conditions change to become quite different from the specific conditions for which the seal was intended. The diagrams show that shaft seal failure is by far the most common cause, or more accurately, symptom of pump system failure. Remember, 90% of pump problems show up as mechanical seal problems, but 90% of seal problems are actually pump problems. So in the following slides, we'll review examples of common causes of failure of mechanical shaft sleeves. On all these slides, there are additional helpful explanatory notes, which you'll see in the hard copy PDF version of the presentation, but I won't read them all in depth. So, operational failures. 40% of sealing device failures are due to operational errors. NPSH, operating dead-headed, dry running, improper venting, and low vapor margin. Mechanical failures contribute to about 24% of all failures. Seal component failures comprise 9% of seal failures. Now, you'll recall 90% of seal failures are actually pump problems. Here's the final 10%. Well, 9% of them anyway. System design failures. 19% of mechanical seal failures due to poor system design. And everything else, 8%. So mechanical seals are a major factor in rotating equipment reliability. They're responsible for leaks and failures of the system, but they also indicate problems that would eventually cause serious damage down the road. Seal reliability is greatly affected by design and operating environment. And the final session, seal troubleshooting. This is really for mechanical seal specialists, not for us pump guys, but it is useful background reading. So these are the things that a seal workshop will want to examine. When you get the hard copy PDF of this course, you'll see quite a few additional notes on these next two slides. Again, this is a specialist area. I'm not going to dwell on it. These are the things a seal workshop will want to examine. And here are some more. Well, that pretty much concludes the fun for today, apart from the Q&A session as usual. I hope you found it useful. I just get now to advertise the next of the short courses, which is going to be on positive displacement pumps. An introduction for those of us, myself included, who are more familiar with centrifugal pumps. 27th of February, that's 4 weeks today. Again, there'll be 2 sessions, one for the Eastern Hemisphere, that's you guys, and one in the afternoon, which will be the morning on the west coast of the USA. The invitation will be published very soon, so put it in your diary. I'm leaving the meeting open for a little while to allow you to post in the Q&A box. So get asking your questions now, and I'll endeavour to answer those that I can right now live in this session. And those that need a fuller answer will be answered within a few days. Anything you think of later, marketing@ruhrpumpen.com, or directly to me, smith@ruhrpumpen.com. Marketing team are standing by to direct your questions to the right person, and they will be sending you the YouTube recording and the PDF of the presentation and of the summarized Q&A from both of today's sessions. If you need a certificate of completion, again, marketing@ruhrpumpen.com, and they'll sort you out. And here, right at the end, 8 slides about Ruhrpumpen to remind you of who we are and what we do. They'll be in the PDF copy of the presentation, so you can peruse them at your leisure. You needn't dwell on them now. So, on with the Q&A. Let me stop the screen share. And let's have a look and see. Oh, we have 12 questions so far. Let's have a look. An anonymous attendee has said, is it possible to change the direction of rotation of the motor at site? I'm not a motor expert, but I don't believe it's an easy fix. I think you'd have to send it to a motor workshop to reverse the direction of rotation. But if you just wired it the wrong way round, that's very common. You just need to switch two terminals and it'll be running the right way. Amir Hasnain says, please explain a little about the use of an eccentric reducer, top side up or top side down. Which configuration shall be used and where? Secondly, how far shall it be installed from the pump suction nozzle? An eccentric reducer would be installed directly on the suction of the pump. It doesn't need to be several pipe diameters down line. It's quite common for it to be right up against the suction of the pump, and it's usual to install it with the flat side on top. And this, if there is a risk of any of NPSH problems and therefore bubbles forming in the pipework, if there are any gases or vapors or cavitation products in the suction of the pump, then we want a flat top so that the air gets chased through the system. If there are potential solids in the did I say the flat side up? No, it will be the flat side. Yeah, and if there are potential solids, then you want the flat side at the bottom so that the solids are flushed straight through. They don't accumulate on the suction side. Faiz ul Islam says, how does instrument air contribute to low flow? Um, I wasn't referring, I think, in the presentation to instrument air, but if air should get into the suction pipework, it would contribute to low flow. Slugs of air aren't going to help it. I may have misunderstood, or I may have not explained very well what I meant. Gabriella Manenti, how can too much oil provide high temperature on a thrust bearing? It does. I had a great story from my pump guru when I was learning pumps. He said he went onto a refinery one day because the pump was running hot, the bearings were running hot, and he went and he had a look and he looked at the oil level and he was chatting away with the maintenance engineers and he got his wrench out and he opened up the drain connection and stood there chatting away to the guys while oil was pouring down into the drip pan. And when it was empty, and they were all panicking. He couldn't understand what he was doing. And when it was empty, he sort of put the screw back in and said, "There you go, you're fine now." And sure enough, the temperature had come down. He said, "When you get a moment, refill it to its not proper level, and you won't have any more problems. Too much oil will cause drag, viscous drag." Mohammed says, for BB3 pump, and after perform, complete OVH and install the pump. The vibration readings are all okay, except the pump horizontal at inboard bearing. It's reading 0.55 inches per second at 1 times normal. We rechecked alignment, retightened all base plate screws, and perform impact test for the base plate. All are normal. What could cause such kind of vibration? Well, that's too precise a question for me to be able to answer that live online. I'm just reading it through to myself again. Um, you need to involve the pump vendor, get him along to do some troubleshooting. I'll look at this in more detail and try and give you an answer, some areas to point you in the right direction in the coming days, Mohammed. Anonymous attendee, brief about open valve start and closed valve startup of discharge and significance of both starts. Well, most pump curves, certainly for most process pumps, the minimum power is at shutoff and the maximum power is at run out. So the kindest way to start a pump that has a curve like that is to start it with under closed valve or slightly cracked open valve. It's the lowest power setting. And then as you gradually open the valve, the power will go up. So that's the kindest way to start a pump with that configuration. But there are some pumps, axial flow pumps in particular, that have a curve where the maximum power is actually at shutoff and the minimum power is at rated point and at run out. So under those circumstances, you'll want to start against an open valve. So that's why you need to have the pump curve there, and follow the operating instructions. Anonymous attendee, please elaborate on pump reverse rotation and its impact on pump and seal parts. Well, if the pump's running the wrong way, it won't pump properly. You won't realize it straight away because it will give some pumping. It will do some pumping, but it won't do it properly. Performance will be down to about 30% of what you'd expect. Now, most mechanical seals are bidirectional. They don't mind which way they go, but some of them are unidirectional. And you have to make sure that they're going in the right direction. So you have to look at the mechanical seal first. What would be common on the mechanical seal would be for the pumping ring to be unidirectional, and then you need to make sure that you got it the right way, or the pumping ring won't be circulating the fluid through the seal and seal system. Sergio Vidal says, "Oh, good presentation. Thanks. Thank you." Ambrish Bajpai says, "How many pumps fail due to lateral and torsional analysis problems?" I don't have a figure, but it won't be very many, because you normally get lateral and torsional analysis problems when they are likely to occur. Analysis will have been done by the pump vendor during the manufacturing phase, during the engineering phase. It's unlikely for there to be a lateral or torsional problem that actually gets through to the field. Sometimes you'll get a pump natural resonant frequency problem, or a system natural resonant frequency problem. That's common because every installation is different and you sometimes can't predict that. And it can commonly be on, especially on vertical pumps, VS6s, VS1s, they can get to site, and once the pump, which was running absolutely fine in the factory, when you get it into site and get it into the pipework system, you hit a natural resonant frequency, and then you need to make some adjustments to the installation. If you place a pump on, say, an FPSO, you obviously don't have grouting. What alternative for that is there? Yeah, that's fine. If it's a non-grout base plate, it'll be a structurally more significant base plate, and it doesn't require grouting. And that's common in some refineries and certainly on offshore installations. So that's absolutely fine. It's been taken into account. Much more rigid base plate. Sunday Azubiojo says, "I would like to have the PDF of the presentation." Yes, everyone who's registered for this session will get in the coming days a YouTube link to download the video, and you'll also get a PDF version of this presentation. Joshi says, what precautions do we need to keep in mind when we're commissioning hot service pumps? Key thing is going to be warming it up properly. And if it's a hot service pump, if you're talking about 200, 300 degrees centigrade, critical that you follow the manufacturer's recommendations. They will tell you in detail in the IOM how to run the hot fluid through the pump and at what rate you should run it through the pump, usually through the drain connection, out through the vent connection or the discharge connection. They'll tell you how to do that, how quickly to do it, and how to make sure it reaches other parts of the, maybe through the mechanical seal as well, to make sure that it's all gradual. Follow the IOM. The general rule is it's going to come in through the drain connection, and out through the vent connection, or out through the discharge connection. That's and at about 40 degrees centigrade per minute to get till it gets up to temperature. Sunday Azubiojo says, is it possible to replace double seal plan with a single seal for a centrifugal pump? Yes, it can be done so. Consult with the mechanical seal supplier. Don't install a seal without checking with a seals vendor that it's suitable for the for the process conditions that you want it to work with. Anonymous attendee says, for vertical pumps, do we need to have any straight length at the discharge of the pumps? For all pumps, we recommend, I've forgotten, is it 3 or 4 straight pipe diameters? It's less critical than having it on the suction side. Suction side, you definitely want 5 diameters of straight pipe, if possible. Discharge, it's less critical, but it's a good idea to have 2 or 3 at least pipe diameters of straight. Hassan Zwida says, what is normally the minimum differential pressure of the mechanical seal chamber and discharge pump line? Usually the mechanical seal will be pretty much at suction pressure. Seal chamber pretty much at suction pressure. Anonymous attendee, is there any straight length requirement for pump suction and discharge piping? Yes, I just covered that. Anonymous attendee again, for horizontal pumps, what is the straight length normally required? Well, again, I just covered that. Anonymous attendee, if the pump is oversized, could the pipe connected to the discharge be rerouted by installing a T and keeping part of the flow to go to its direction and connect part of that flow to the pump inlet line? Excuse me a second. Yes, that would be quite a common thing to do, but the important thing, if you are take the amount of flow that you want to the process and the remainder goes through that T, maybe through an automatic recirculation valve back to the suction tank, not to the suction line of the pump unless it's well upstream. You don't want to circulate flow through the pump. So if you're going to recirculate it back to the suction vessel would be ideal. Otherwise, to the suction line, but well upstream. Monis Akhtar says, does Ruhrpumpen have low flow, high head models like 100 gallons per minute and 1350 feet? Yes, we can do that with VS6s. We also have a pump called a combi tube, which is a pitot tube pump. I might be doing a presentation on those pumps in the coming months, and they are low flow, high head. 100 gallons a minute, 1350 could also be in the range for a Sundyne pump, an OH6 pump, integral geared high speed pump. Anonymous attendee, can pumps start having vibration problems randomly during normal operation, i.e. not during commissioning? Well, yes, if there's been if at any time a change in the process conditions can cause a problem, and that's why you need to analyze everything. So what's changed? what are we doing in the system that's suddenly different? That's the troubleshooting. Get your pump professional in to help you. Stefan Bachmann says, do you have any special recommendation for startup of mag drive pumps? Nothing springs to mind immediately, but that would be a matter of really of reading the IOM manual. It'd be slightly different from a mechanically sealed pump. Mohammed Abu Shala says, great session. Thank you. How could I register for the following sessions? Am I going to receive an invitation link? Well, if you received an invitation link for this one, yes, you'll receive the link for the next one as well. Anyone who registered will be added onto our list for the next one. Maciek Petrowski, did I get that even close? Customer needs flow margin usually can be 20% and use a throttle valve to reduce this. How great can this margin be? Yeah, I mean, pumps are usually being operated. I mean, virtually every pump spec has built in safety margins, so it's not unusual for the rated condition to be 20% higher than the actual position. This is okay. You have to answer it case by case. If the pump rated flow, which is 20% higher than expected flow, if your point is to the right of best efficiency point, that'll be ideal because once you've got 20% off that, you'll be just to the left of best efficiency point, perhaps. But what you want to avoid is oversizing a pump such that you're running well back to the left. If your pump's too large, you need a smaller pump. Mohammed Abu Shala says, for high flow rate pumps, technically, is it better to install a single stage pump or is it better to install multi-stage pump? For high flow rate pumps, technically, is it better to install a single stage pump or is it better to install multi-stage pump? Well, whether you need a single stage or multi-stage pump really depends on the pressure rather than the flow. So if you've got a high pressure pump, you'll either need to run at high speed to get the required head, or have a multi-stage pump. BB3, BB5 pumps, these are very reliable pumps. They're being used in the oil pipeline business all the time, and they've been well established. So there's no reason not to be using those. Probably better than having a high speed pump for those operations. But it's very hard to answer that question because it's really how long is a piece of string? Can be that long. Yeah, I would need to have a look at the precise operating conditions you want, and then we'd be able to make a recommendation, as would any other pump manufacturer. Anonymous attendee says, is Plan 11 suitable for liquids with hot discharge temperatures? Would it be more suitable to have cooling water connections? My pump supplier has specified Plan 11, and the discharge is water under pressure at greater than 100 degrees centigrade. I'm guessing that anonymous attendee is a seal vendor, and if he's the pump vendor, I mean, I'm tending to agree with you that if it's water under pressure at 100 degrees centigrade, there probably should be some cooling to that stuffing box, or better, perhaps a Plan 23 to cool the process fluid, the water in there. I would go back to the pump supply. I mean, you're the experts on mechanical seals. You should go back to the pump vendor and say, you've specified an 11, but in my opinion, 23 would be what you need for this one. Ambrish Bajpai says, do vertical pumps such as VS4 need to undergo modal analysis if the length of the pump is around 4 meters, including motor? Yes, I think it could well be that about 20% of vertical pumps in new installations that haven't been checked out before, they will have a, a critical speed problem, a natural resonant frequency problem. About 20% of new untried installations will have that. And it's usually a fairly simple thing to either stiffen or soften the system to get you away from that natural resonant frequency. I think I'm going down with a cold. Well, that appears at the moment to be all the questions. There were 28 of them, and we had 140 of you on board at one stage today, which is very good. Thank you for all attending. So I will call it a day. It's 9:05. We've overrun by 5 minutes here. So thank you very much again for attending today. I enjoyed preparing it and presenting it. I hope you found it useful, and I look forward to seeing you on the 27th of February for the next session. Bye-bye. See you then.